In part 1 of this two-part series on Europe's path to real space independence, I covered a European space station and reasons to locate it in a 60-degree inclination orbit. In this second part, I want to cover the launch site and heavy lift vehicle for deploying and sustaining a space station over the coming decades. Commercial European launchers will operate from high-inclination spaceports in Europe. Sun-synchronous orbits and other high-inclination orbits are in high demand from customers. This is because Earth imaging, surveillance, and coverage missions all require this type of orbit. Unfortunately, Europe's main spaceport is sited at only 5 degrees latitude, barely above the equator. While equatorial orbits were once popular, that isn't the case now, and this spaceport is poorly aligned with customer demand and has limited capability to deploy orbiting space stations to high-inclination orbits. Although, as I'll show later, Europe's main spaceport and Ariane 6 can deploy a space station to a 60-degree orbit. After watching this video, please drop your thoughts and opinions in the comments section below, and we can discuss live at the weekend. I host a live stream every weekend recapping this week's videos and the space news, reading out many of the comments and chat messages I receive. I hope you can join this weekend. Okay, let's talk about Europe's launch pad and the future heavy lift rocket. A future heavy lift rocket should fly from Europe. The launch pad and rocket supporting a European-led space station should be in Europe. While this seems obvious, it's not the case at the moment. Every part and component of the rocket should be produced in Europe, otherwise foreign governments can leverage technology dependency to pressure Europe for geopolitical or economic reasons. While the technology angle is important, Europe has a far bigger security risk that no one wants to talk about. The problem with French Guiana, Europe's spaceport. Long logistical routes compromise security. Any overseas route could potentially result in loss of satellites by hostile actors. Transporting military satellites from mainland Europe well over 8,000 kilometers to the European spaceport in French Guiana represents a huge risk. If hostilities were to take place between Western Europe and Russia, then it's likely Russia would target shipments from Europe headed to French Guiana. Satellites are essential for surveillance, Earth observation, and communications. Europe has for far too long ignored this glaring vulnerability. In the last 4 years, somewhere between 30 to 50 accidents have occurred at European bases, military facilities, and factories. The reality is Russia is involved in hybrid warfare against Europe. Russian naval assets have been seen loitering near critical European infrastructure, including undersea internet cables, oil rigs, power cables, and other maritime infrastructure. Europe has to stop shipping expensive and irreplaceable satellites halfway across the world to launch them. The solution: launch from Europe. In part 1, I proposed a 60-degree inclination for a European-led space station as it aligns with current launch infrastructure in Europe, enabling rockets to fly with zero or minimal orbital plane changes, providing maximum payload capacity to an orbiting station. Siting a future heavy lift launch complex in Europe further centralizes all launch operations, cutting logistical routes, shortening time to launch, and eliminating time zone differences between the launch pad and mission control centers. European space startups working on orbital rockets already plan to fly from high-latitude spaceports. As of today, Rocket Factory Augsburg will fly from Saxford in Scotland, and ISA Aerospace flew its first mission from Andøya Spaceport in Norway. These spaceports have a latitude of 60 and 69 degrees. European launch sites must minimize overflight of populated areas while providing highly efficient access to customers' preferred high-inclination orbits. Both sun-synchronous and polar missions are more efficiently launched from high-latitude spaceports. Europe has no mid-latitude spaceports because rockets would have to fly over highly populated areas of Europe. In the event of a launch failure, debris would rain down over a wide area, potentially hitting people or damaging buildings. It would be nearly impossible, given European safety regulations, for a spaceport to get approval to fly from a mid-latitude location. The majority of commercial European launch providers intend to fly from a high-inclination spaceport within Europe. Why Europe needs a strategic moat? European space startups need to be protected to grow, otherwise they will lose to better funded and more mature US launch providers. The US has poured tens of billions of dollars into its space industry through NASA, US Space Force, DARPA, Department of Energy, and other agencies. Add to that I-HAB regulations, which make it very difficult for European companies to enter and compete on a level playing ground in the US. Even collaboration with European companies is heavily restricted. This effectively protects the US space ecosystem from European competition. The US is protectionist and effectively blocks non-US companies from competing in its domestic market. A sovereign European launch capability can benefit from a strategic moat by taking advantage of Europe's geography. High-latitude missions incur penalties to US launch providers flying from mid-latitude spaceports in the continental US. This is not to say US rockets, especially medium-lift vehicles, cannot reach high-inclination orbits. Just they would have to expend extra fuel to do so, reducing payload mass. Why Ariane 7 should fly from a high-latitude spaceport in Europe? While Ariane 7 is likely some time off, Europe should be planning for its next launch vehicle, this time a vehicle optimized for launching from a European high-latitude spaceport. Let's call the vehicle Ariane 7 and list why all launch operations should be carried out within Europe. Centralizing all European space operations, including launch, shortens supply lines, provides improved security, and is more cost efficient. A European launch site strengthens strategic independence and aligns better with commercial European launch vehicles which already plan to launch from European spaceports. Long-term cost savings make the vehicle more cost competitive in the global market. In addition, large mass space station modules or infrastructure needs to be deployed close to the final orbital inclination. This is because, unlike spacecraft or capsules, which can efficiently change orbital plane in space, massive objects cannot. For instance, large solar power satellites that beam gigawatts of solar energy down to Earth could be deployed into highly elliptical orbits with an orbital inclination of 63 degrees. Future heavy lift vehicles flying from European spaceports would allow direct or near-direct orbital injection with little or no plane change. Ariane 7 would need to be designed to handle strong winds and freezing temperatures found at higher latitudes. A new spaceport would need to be constructed to support a heavy lift vehicle. This location needs to be defended from the air and sea due to its critical importance to European security. This will affect the choice of spaceport. This is a reason to choose Scotland as a location for a heavy lift launch, ideally on the UK mainland for shorter logistical routes. There is a strong space sector in the UK, with the UK government likely funding construction of a launch pad in the country. While this future plan, even if approved, would take a decade or more to achieve, can we build a European space station in orbit now using existing infrastructure? The answer is yes. Plan for European space station using Ariane 6. Ariane 6, launching from French Guiana, can deploy all modules needed for a European space station. The way to do this is by launching on a highly elliptical orbit. This results in the payload at the furthest point from Earth, or the apogee, moving much slower than it would in a circular orbit. Using a powerful kick stage at the apogee can change the orbital plane for a much lower cost than using the rocket itself. This is because the delta V required depends on the velocity. Slowing the payload down reduces the fuel needed for the plane change. With this approach, modules of up to 10,000 kilos can be successfully deployed to a 60-degree inclination. This only leaves one technical issue left: solving the I-HAB mass problem. The I-HAB module is heavy, likely 10 tons or more once outfitted. Even with an optimized orbit and kick stage, we need to slim down this module. Luckily, that isn't that difficult to do. This is because the I-HAB was built to withstand the lunar orbit environment, not benefiting from Earth's magnetic field. This allows us to strip between 800 to 1500 kilos in radiation shielding of the module. In addition, we can remove life support systems, crew quarters, interiors, power and thermal systems, and structural margins. This brings a stripped down I-HAB module down to around 8 metric tons, which the Ariane 6, in its most powerful configuration and using a kick stage, can deploy into a 60-degree inclination orbit. With that, we now have solved all the technical problems. Let's have a look at the launch manifest. We'll take full advantage of existing structures and fly the modules in the optimum manner. All of these flights use Ariane 6-4 with a kick stage for orbital plane change. First, we deploy a power and propulsion unit along with Canadarm3. We add the robotic arm to the power and propulsion unit so it can be used for assembly for all future flights. The second flight deploys the core living module, a stripped down I-HAB module that's already built. The next two flights deploy inflatable expansion modules. And finally, a node module to add additional docking ports and for outfitting of the I-HAB with all equipment and systems needed. With only 5 flights, a 36-ton space station with 550 to 700 cubic meters of habitable space, complete with a robotic arm, is established. Crew can now be permanently stationed at this facility. Until Europe has a crew vehicle, it would have to rely on Crew Dragon for visiting the station. One thing to note is that there is no constraint on launch vehicle availability. Ariane 6 has launched twice already this year, and the station can be fully assembled with only 5 flights. Space station hardware and funding is a limiting factor to deployment speed. Final thoughts. The plan to relocate Europe's heavy lift launch complex in Europe saves money, time, and reduces the security risk of siting critical infrastructure thousands of kilometers away from Europe. A European launch site and heavy lift rocket operating from a high-inclination spaceport provides maximum payload capacity to an orbiting space station and enabling heavy infrastructure in sun-synchronous and polar orbits. In the meantime, a solution to deploying a European space station from French Guiana using Ariane 6 is suggested. Do you think this assembly plan using Ariane 6 is feasible? What do you think of operating the next heavy lift rocket from Europe? Leave your thoughts and opinions in the comments section below. Thanks for watching. If you enjoyed this space video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Watch the weekly live stream to see the images, clips, and slides from this week's videos. It's a live Q&A on this week's space topics where I read out some of the best comments. The more people join, the more fun the live stream is. Be sure to like and subscribe so you will see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.